Hi all, today we are going to study about armature reaction of DC machines. The basic definition of armature reaction is the effect of armature flux on the main field flux. Armature magnetic field has two main effects. One is demagnetization and the other is cross magnetization. Demagnetization leads to reduced generated voltage, whereas cross magnetization leads to sparking at the brushes. So in this slide, the introduction of armature reaction or the definition of armature reaction and their effects are mentioned. We are going to study about them in detail in the upcoming slides. So the basic definition of armature reaction all of you must know. That is, it is defined as the effect of armature flux on main field flux. I very well know that you didn't understand anything. Once when we finish today's class, you will get a clarity on the definition of armature reaction and their effects. For understanding in detail about armature reaction, we will be considering a bipolar generator. Bipolar generator means a generator which is having two poles as indicated in this figure. There are only two poles, that is this north pole and the south pole. Main flux is actually the flux which is passing from this north pole to south pole. In this diagram we have considered the situation that there are no current flowing through this armature conductors. Armature conductors are being represented by this rounds here. See, this all are the armature conductors, and we have considered the case of no load. No load means there is no current flowing through this armature conductors. A line connecting through the centers of this north pole and south pole is actually called as the polar axis. Here the flux, the main flux is actually distributed uniformly across the polar axis. That is, if you consider a line joining through the middle of this north pole and south pole, then you will be able to see the distribution of this main flux is actually symmetrically across this polar axis. The line perpendicular to this polar axis is called as interpolar axis. It is also said to be geometrical neutral axis. It is represented here. So geometrical neutral axis is actually a line which is perpendicular to the line joining through the middles or through the centers of this north pole and south pole. In order to understand the basic definition of armature reaction, we have considered a no load DC generator here, and the distribution of main flux is shown here. If you see in this diagram, you will find that the brushes are being placed over the armature, but in real practice it's not like that. Brushes are always placed over the commutator. This is actually the armature core and these are the armature conductors. These two are the brushes. So you may feel that the brushes are being placed over the armature. It's not like that. For the ease of understanding the concept of armature reaction, it's just shown like that. These brushes always lie along the magnetic neutral axis. So you must know, what do you mean by a magnetic neutral axis? Magnetic neutral axis is the axis along which no EMF is generated, as this axis is moving parallel to the flux lines. The position of magnetic neutral axis is not constant. They keep on shifted. Only in the case of a no load DC generator, the magnetic neutral axis will overlap with that of the geometrical neutral axis. Don't get confused with the definition of geometrical neutral axis and magnetic neutral axis. Both are different. Magnetic neutral axis is defined as a line which is perpendicular to the line joining through the centers of this north pole and south poles. The position of geometrical neutral axis is always fixed. whereas magnetic neutral axis is defined as the line along which no EMF gets induced, as this line moves parallel to the main flux or the flux lines. Brushes are always placed along the magnetic neutral axis. In the case of a no-loaded DC generator, both this magnetic neutral axis and geometrical neutral axis overlap each other, or the magnetic neutral axis coincides with that of the geometrical neutral axis. Initially, we have considered the distribution of main flux in a no-load DC generator. In this slide, we are going to see the distribution of armature flux alone. As you see in this diagram, the main flux is not represented here, or the distribution of flux lines, that is main flux lines, are not shown here. Current is flowing through the armature conductors. If you see the direction of current in the conductors placed at the left side of the geometrical neutral axis, that is this conductors, in this conductors the direction of current is into the conductor, whereas if you see those conductors which are placed at the right side of the geometrical neutral axis, in this conductors the direction of current is out of the conductors. The direction of current which is into the conductor is represented by a cross here, and the direction of current which is out of the conductor is represented by a dot here. So in this case, we have considered only the armature flux. There is no main flux. As you have studied in your basic electrical engineering course, whenever a conductor is carrying current, there occurs a magnetic flux around it, and the direction of this magnetic flux is represented by Maxwell's corkscrew rule. It is also said to be right hand thumb rule. We can get the direction of armature flux by applying corkscrew rule in these conductors. Conductors which are under the influence of north pole is carrying current into them. Right hand thumb rule can be applied by placing your right hand in the thumbs up position. The thumb of the right hand indicates the direction of current, and the curl of the fingers represents the direction of magnetic flux. So if you see here, in this conductors which are under the influence of north pole, the direction of current is actually into the conductor. So you have to point your thumb into them. Then the curl of the fingers, that is actually in the clockwise direction, represents the direction of armature flux. In those conductors which are lying under the influence of south pole, this will be exactly opposite to what happened under the north pole, or the direction will be definitely opposite to that under the north pole. Here you have to point the thumb in the outward direction. Then the curl of the fingers, which is actually in the anti-clockwise direction, represents the direction of armature flux. We have seen the distribution of armature flux alone and the distribution of main flux alone. The direction of main flux is same as that of the direction of main field MMF. It is represented by a vector here, OFM. This the M in the F indicates that it is main field flux. In this diagram, if you see, the maximum crowding of the flux lines, that is armature flux lines, is seen here. So we consider that as the direction of armature flux, which is actually vertically downwards. So this can be considered as the direction of armature MMF. The direction of armature MMF is identified by considering a system with armature flux alone, and the direction of main field MMF is identified by considering a system with main field alone. Next we are going to study the effect of this armature flux. What effect does this armature flux creates on the main flux? That is the actual definition of armature reaction. Before understanding the effect of armature flux on main field, one must know the meaning of the terms trailing pole tip and leading pole tip. If you see in this diagram, this pole tip and this pole tip, these two pole tips are said to be trailing pole tips, whereas this pole tip and this pole tip, these two pole tips are said to be leading pole tips. Here we have supposed that the armature is rotating in clockwise direction. So when the armature is rotating in the clockwise direction, those conductors which are under the influence of north pole will be moving towards the south pole, whereas those conductors which are under the influence of south pole will be moving towards the north pole. So if you are looking here, you will be able to see this conductors will be leaving the north pole through this pole tip and they will be entering the south pole through this tip. Similarly, if you are looking here, those conductors which are under the influence of south pole will be leaving the south pole through this pole tip and they will be entering the north pole through this pole tip. The pole tips through which the conductors are leaving the poles are said to be trailing pole tips, and the pole tips through which conductors are entering the poles is said to be leading pole tips. So if you see in this diagram, these two are the trailing pole tips and these two are the leading pole tips. Now we are going to see the effect of armature flux on main flux. In this figure, the first diagram is representing the main flux alone, second diagram is representing the armature flux alone, and the third diagram represents the effect of armature flux on main flux. For the ease of understanding, we have considered only two armature conductors. One is under the influence of north pole and the other is under the influence of south pole. By using right hand thumb rule, we very well know that in this conductor the direction of current is clockwise and in this conductor the direction of current is anti-clockwise. So if you are looking at the top side of this conductor, the armature flux over here will be aiding the main flux, whereas if you see the bottom side of this conductor, the armature flux will be opposing the main flux. So definitely there occurs a crowding of the flux lines at the top of this conductors and weakening of the flux lines at the bottom side of this conductor. Similarly, if you are looking in this conductor also, as the direction of current in this conductor is opposite, the magnetic lines of force are also in opposite direction. At the top side of this conductor, the armature flux will be opposing the main flux, whereas at the bottom side of this conductor, the armature flux will be supporting the main flux. So in effect, I can say at the top side of this conductor, there is a crowding of magnetic flux, whereas at the top side of this conductor, there is weakening. Next, considering the bottom sides of the conductors, at the bottom side of this conductor, there is weakening of flux lines, and at the bottom side of this conductor, there is strengthening of flux lines. So I can say, due to the effect of this armature reaction, there occurs a crowding of flux lines at the trailing pole tips. These two are the trailing pole tips. This is the trailing pole tip of north pole and this is the trailing pole tip of south pole. And there occurs weakening of flux lines at the leading pole tips. This is the leading pole tip of south pole and this is the leading pole tip of north pole. In the previous slides, we have clearly indicated the main field MMF direction and the armature MMF direction. In this slide, we will be seeing the resultant MMF. This vector represents the main field MMF, this vector represents the armature MMF, and OF represents the resultant MMF. The magnetic neutral axis always lies perpendicular to the magnetic lines of force. So if you see in this figure, the magnetic neutral axis has to be perpendicular to the resultant MMF. Initially, when there was no armature flux, the magnetic neutral axis position was this. But due to the effect of armature flux, the resultant MMF is towards this direction, that is along OF, which causes the magnetic flux lines to flow like this. As the magnetic neutral axis always lies perpendicular to the resultant flux, it results in the shift of magnetic neutral axis from this position to this position by an angle theta. In simple words, we can say the magnetic neutral axis must be always perpendicular to the magnetic lines of force. So in this case, you will be able to see the magnetic neutral axis is lying here. But due to the effect of armature reaction, the magnetic lines of force is getting modified and they are moving in this particular direction. There is a slight deviation in the flow of the magnetic lines of force. So the magnetic neutral axis has to be perpendicular to this magnetic lines of force, which is being indicated here. So now it's very clear that due to the effect of armature flux on the main flux, the flux lines are getting redistributed, which results in the shift of magnetic neutral axis. Due to the shift of this magnetic neutral axis, the position of these brushes are also getting shifted, as the brushes always lies along the magnetic neutral axis. Due to the shift in brush position from this geometrical neutral axis, or that was the old position of magnetic neutral axis, to the new position of this magnetic neutral axis, there occurs a redistribution of current in the armature conductors. Before, we have seen that all those conductors which are towards the left side of the magnetic neutral axis were carrying the current into the conductor, and those which were at the right side of the magnetic neutral axis were carrying the current out of the conductors. Now also the same condition persists, that is those conductors which are at the left side of the magnetic neutral axis. Now the left side of the magnetic neutral axis is this conductors carries the current into them, whereas at those conductors at the right side of the magnetic neutral axis. Now the right side of the magnetic neutral axis consists of this all conductors, will carry the current out of the conductors. You will be able to see here. If you see in the diagram considering armature flux alone, these two conductors were carrying current into the conductor, whereas these two conductors were carrying current out of the conductor. But due to the effect of armature reaction, there occurred a shift in the position of magnetic neutral axis, which results in the shift of the brush position. This caused a redistribution of current. Now if you see in these two conductors, current is carrying into them, and in these two conductors current is moving out of them. So it's clear that the current has been redistributed in these conductors. Now let's see the effect of armature flux in this new position of magnetic neutral axis. Now we are considering the effect of armature flux alone. The armature flux line seems to be crowded in this region, so we can consider this as the armature MMF direction, which is represented here. See, the direction of armature MMF will be definitely towards this direction, which is represented as a vector here, OFA. If you are splitting this OFA into two components, one is OFD and the other is OFC, definitely this vector OFD is actually opposing the main flux. The main flux direction is from north pole to south pole. So definitely this OFD is exactly opposing the main flux. This results in demagnetization. The demagnetization effect caused by this component of the armature flux results in reduced magnitude of main flux. In the last class we have studied the derivation of EMF equation, that is induced EMF. or generated EMF is equal to 5 PNZ by 60A. So definitely due to the effect of this armature reaction, that is one harmful effect is demagnetization. So due to the demagnetization effect of this armature reaction, the magnitude of main flux has been reduced, which further results in the reduction of magnitude of generated EMF. This is what I have mentioned in the first slide. One of the effects of armature reaction is it demagnetizes or weakens the main flux. Demagnetization leads to reduced generated voltage. The second component is OFC. This component actually distorts the main flux and it results in cross magnetization. Actually, this component simply cuts the main flux lines which are flowing from north pole to south pole, hence it is producing the distortion effect. As it is simply cutting the magnetic lines of force from north pole to south pole, it is also said to be producing cross magnetizing effect. So it's very clear that the effect of armature flux on the main flux disturbs the main flux, which causes a shift in the magnetic neutral axis, and this leads to a shift in the brush position, which further causes the redistribution of current in the armature conductors. Considering the armature MMF after redistribution of current and splitting them into two components, OFD and OFC, component OFD will be opposing the main flux and component OFC will be cutting the main flux lines. So this component OFD causes demagnetization effect and this component OFC causes the cross magnetization effect. Both these are undesirable effects. Demagnetization results in the reduced generated voltage, whereas cross magnetization results in sparking at the brushes. Hopefully the concept of armature reaction is clear for you. In the next class we will study about various characteristics. Thank you.